Welcome to the lecture on laws of exponents and scientific notation. Today we're going to talk about the various laws of exponents, practice using them, and then use them to solve expressions involving exponentials. So let's start by reviewing the product rule. What the product rule says is that if you have two things with the same base, then you can add their exponents. So a to the m times a to the n equals a to the m plus n. For example, if I have 7 to the third times 7 to the fourth, that becomes 7 to the 3 plus 4, or 7 to the seventh. The quotient rule says that if you have two expressions with the same base that you're dividing, then you're going to subtract their powers, the top power minus the bottom power. So if I have 2 squared over 2 to the fifth, then this becomes 2 to the 2 minus 5, the top power minus the bottom power. 2 minus 5 simplifies to a negative 3. We're going to talk in just a minute about negative exponents, but what this becomes is it becomes the reciprocal, 1 over 2 to the third. So another way of thinking about how you can take 2 to the second over 2 to the fifth and write it directly as 1 over 2 cubed is to take the bigger power minus the smaller power, so 5 minus 2 is 3, and put that answer in the place where the larger power was. So since the larger power, 5, was in the denominator, 5 minus 2, I'm going to put that answer in the denominator as well. Doing that larger power minus smaller power helps you avoid dealing with any negative exponents at all. So we'll practice that some more later. Zero exponents. Anything raised to the 0 power is going to equal 1. So negative 2 raised to the 0. Notice there are parentheses involved here, so both the negative and the 2 are being raised to the 0 power, so the entire quantity goes to 1. Power rules. These are the rules that are kind of like distributing powers. If you have a to the m raised to the n, so I like to think of this as a power to a power, then you get to multiply these two powers together. So this becomes a to the m times n. A lot of times when I see parentheses, that helps remind me that I should be multiplying powers. As opposed to up here when we did the product rule, there were no parentheses, so I was adding exponents. So if I saw x squared, quantity cubed, multiplying 2 times 3 makes this x to the 6th. In the next two power rules here, I also have parentheses, but this time what I'm going to be doing is sort of distributing that power across to every term that I see. So if I have a times b raised to the m, I can distribute that power of m to both the a and the b and get a to the m, b to the m. And the same is true for division. If I have a over b raised to the m, I can take a to the m over b to the m. So for example, if I have 3k quantity to the fourth, I'm going to distribute that fourth power. This becomes 3 to the fourth and k to the fourth. And 3 to the fourth is small enough that you could probably do that in your head. 3 to the fourth is 3 times 3 times 3 times 3, which makes this 81 k to the fourth. I didn't do that up here because 7 to the seventh is a pretty large number that I probably wouldn't know off the top of my head. 1 over 2 cubed, if you wanted to change that, 2 cubed is 2 times 2 times 2, so this could also be written as 1/8. My rule of thumb is usually if the power and the base are small enough that I can do it in my head, then I figure it out. If the power and the base are too large, then I just leave it in exponential form. Let's go back to our 2 over 3 quantity squared. If I wanted to distribute this power of 2 across, I'm going to distribute it to the top, 2 squared, and also to the bottom, 3 squared. 2 squared turns into 4, and 3 squared turns into 9, so the whole thing is 4 ninths. Now notice on these power rules, we are distributing the power as long as you have a times b or a divided by b. You only get to distribute a power across multiplication and division. If this was addition or subtraction, for example, a plus b to the m, that does not apply. You cannot distribute a to the m and b to the m and get the right answer. What you would be missing there are a bunch of middle terms. when we talk about distributing and the FOIL process, you would need to FOIL out a plus b quantity to the m, and that's going to give you a bunch of middle terms that this right side over here doesn't have. So distributing powers does not apply to addition or to subtraction. It only applies to multiplication and division. Okay? Negative exponents. Let's take a look at some of those. What a negative exponent does is it basically takes a reciprocal. So if you have a negative exponent, a to the negative n, that's going to flip it over, because that's what a reciprocal does. It's going to flip it down into the denominator, and it makes that exponent turn positive. If you have a negative exponent starting in the denominator, then you can flip it up to the top, and that exponent becomes positive. So negative exponents kind of just flip you over. So if I have 5 to the negative 3, right now that's in the numerator, because you could think of this as being over 1. So I'm going to flip it down to the denominator. Once you do that flip, the power becomes positive, and this just is going to have a factor of 1 on top. And 1 over 5 cubed becomes 1 over 125. If I have 1 over x to the negative 3, the negative exponent is starting in the denominator, so I can flip it up to the top, and when I do that flip, it turns positive. So this just turns into x cubed. So what we're going to be doing next here is putting all these rules together to simplify expressions involving exponents. These are sort of the steps that you would want to follow to help make the problems a little bit more manageable. Step 1 is to distribute your powers over your products and your quotients. In other words, you want to get rid of any parentheses that you might have in the original problem first. When you're doing that and you're distributing those powers, if there are any powers on the inside of the parentheses and a power on the outside, you're going to be applying your power to a power rule, which basically says you can multiply those powers together. Step 3. If any of your expressions have negative exponents, then this is where you're going to flip them around. So if you have a negative exponent in the denominator, you're going to flip it up to the top. If you have a negative exponent in the top, you're going to flip it down to the bottom. Step 4, once you have all the negative exponents gone, you're going to either add or subtract your exponents based on whether you have a product or a quotient rule. And then the last step is going to be to do any numerical calculations on the coefficient numbers. So this would be like cubing 2 or dividing your coefficients out front, simplifying the numbers. Alright, so let's try some out here. If I have n squared times n to the 4th times n, then this becomes n, base n, they all have a common base, and my product rule here says that I can add these powers. And remember, n, this last term right here, has an implied exponent of 1. So 2 plus 4 plus 1 is going to give you n to the 7th. On the next example here, we have some parentheses, so we want to sort of get rid of them first. Since there's no powers outside here to be distributed, then I'm just going to get rid of them by doing my multiplication that's in between, that's implied. So I'm going to take the number times the number. 10 times negative 3 would be negative 30. And the variable times the variable, you want to make sure they have the same base. A squared times a to the 4th, remember, same base, multiplying the bases, you get to add the powers. So 2 plus 4 gives me a to the 6th. Okay? On the next example, we have parentheses again, but we do have powers on the outside. So on these, we're going to apply that power to a power rule. We have y to the 4th raised to the 5th. We get to multiply these two powers together. 4 times 5 gives me y to the 20th. And applying power to a power rule here, 3 times 5 gives me y to the 15th. Now that those parentheses are gone, I'm just multiplying my bases, and my product rule says that I can add exponents in that case. So this becomes y to the 35. On the next example, we have a lot more stuff going on. We do have an outer power on each of these sets of parentheses that we want to distribute across first. So the first thing I'm going to do is distribute my cube. Now make sure you distribute your cube to every term, including the coefficient 3, the x, the y, and the z. Any term inside, like these x's and y's that already have powers, you're going to be applying that that power rule, which says we get to multiply the inside power times the outside power. So for example, 3 doesn't really have an exponent. There's an implied 1 there. So this 3 is going to get cubed. For now, I'm just going to write that as 3 cubed. We'll figure out what that is a little bit later. When I get to the x, I do have an exponent already there. So 4 times the 3 on the outside makes this x to the 12th. And then this y has a second power. 2 times 3 becomes y to the 6th. And z doesn't have an exponent, so it's just going to get cubed. Now we're going to do the same thing for the second set of parentheses. Distributing that 5 to the y gives me y to the 5th. Distributing that power of 5 to z to the 4th and multiplying 4 times 5 gives me z to the 20. Now we're not done here because I see a couple terms with the same basis. I've got 2 y's and I also have 2 z's. Remember, this is multiplication going on, so we're going to be applying our product rule, which says if you have the same base, then you can add the powers. So this 3 cubed, I'll leave it out front for now. X to the 12th doesn't have any other x terms to combine with, so that one's going to stay put. But when I get to y to the 6 times y to the 5, when I add 6 plus 5, that gives me y to the 11th. And z cubed times z to the 20, 3 plus 20 gives me 23. The last thing here that I would do, I've got my x's together, my y's together, and my z's together. The last thing I'm going to do is do my numerical computation, 3 cubed. 3 times 3 times 3 is 27. So we get 27x cubed, y to the 11th, z to the 23. And there's my solution. Okay, on the next example, same kind of thing. We've got parentheses with an outer power, so we're going to want to distribute the power across. On this first example here, this first set of parentheses, it's easy to overlook that negative. But when you take this power 4 and you distribute it, you need to distribute that to the negative as well as the t as well as to the s. Now, a negative raised to the 4th is really like a negative 1 raised to the 4th. And remember that if you have an even number of negatives, that turns into a positive. So negative 1 to the 4th is just going to turn into a positive 1, which you wouldn't even really need to write down. So that takes care of the negative. T is going to get raised to that 4th. And s to the 6th, when you raise that to the 4th, you multiply those power to a power, so this becomes s to the 24. So that's my first set of parentheses. On the second set, I'm going to do the same thing. Raise the negative to the cube, t cubed to the 3rd power, and s to the 5th to the 3rd power. So negative 1 cubed is an odd number of negatives, so that's going to stay a negative. Let me wrap this first set in parentheses still until I figure out what's in the second set of parentheses. So negative cubed stays negative, or negative 1. T to the 3rd raised to the 3rd, multiplying those powers of 3. 3 times 3 is 9, so this will be t to the 9th. And s to the 5th raised to the 3rd, multiplying those powers, gives me s to the 15. Now the reason I put those parentheses in there is so that if I didn't have them, it might be misleading. I might see this minus here and think that I'm supposed to be subtracting this term with this term, and that's not really the case. I want to be multiplying the two together. So we're going to multiply coefficient times coefficient. Positive 1 times negative 1 is going to stay negative 1. You don't really need to write that 1 in there, so I'm just going to write it as a negative out front. T's times t's, t to the 4th times t to the 9th. Here is that product rule. Remember that if you have the same base and you're multiplying, you're adding exponents. So 4 plus 9 will give me t to the 13th. And then s times s, adding exponents again, 24 plus 15 is 39. So my final solution, negative t to the 13th s to the 39. Next example, we have a big fraction raised to the 4th power. Remember that we do get to distribute powers across division. So I'm going to distribute the 4 to the 6, the x, the y, and the z. Now 6 doesn't have a power on it already, so it's just going to get that 4th power. X cubed raised to the 4th is a power to a power, so we want to multiply 3 times 4 and get 12. 9 times 4 would be 36, so this will be y to the 36. And 5 times 4 is 20, so this will be z to the 20th. Now I don't really have any more x's, y's, or z's to combine. There's only one term of each. If you want to evaluate 6 to the 4th, 6 times 6 times 6 times 6, that's kind of a large number. So you could either leave it as an exponential or you could use your calculator to figure it out. 6 to the 4th turns out to be 1,296. So this is x to the 1,296, x to the 12th, y to the 36, all over z to the 20th. Okay, next example, same thing. We're going to distribute this 3rd power to this quotient. Make sure you distribute it to the negative, the 2, the x, the y, and the z. So a negative raised to an odd power is going to stay negative. 2 raised to the 3rd, for now I'm just going to leave that as 2 to the 3rd. X to the 2nd raised to the 3rd, power to a power, so we multiply, gives me x to the 6th. And y to the 4th cubed, 4 times 3, gives me y to the 12th. In the denominator, 3 times 3 is 9, so we have z to the 9th. There's no x's, y's, or z's to combine, so the only thing really here to figure out is 2 cubed. 2 times 2 times 2 is 8, so this is negative 8, x to the 6th, y to the 12th, over z to the 9th. Alright, now we're going to do a few examples with some more of these negative exponents. We haven't really done any of those yet. So if I see the expression 2y to the negative 3, oftentimes your instructor or your textbook will ask you to write your answers using positive exponents only. So this would not be correct because I have that negative 3 power. So what we want to do is remember that negative exponents flip, and since this y to the negative 3 is in the top, if you think of this as being over 1, all we have to do is move it down to the denominator. When you do that flip, the power now becomes positive, and since this 2 did not have a negative exponent on it, it's just plain old 2, that 2 is going to stay put in the numerator. So your final answer is 2 over y cubed. And there's no more negative exponents. If I have 1/2 raised to the negative 4, we can use a shortcut here. Instead of flipping over, thinking of this as being over 1 and flipping the entire thing down, we could do that, but that's going to leave us with a really messy, complex fraction. So as a shortcut, what we can do is flip on the inside of our fraction first. So instead of having 1 over 2, we can flip that over to 2 over 1 and change the outer power to a positive 4. Now I wouldn't leave my answer like that because 2 over 1 is just 2. So 2 to the 4th is something we can evaluate. 2 times 2 times 2 times 2 is going to be 16. So if you have a fraction on the inside raised to a negative exponent, as a shortcut, sometimes it's easier to flip that fraction around inside and change the outer power to a positive. On the next example, I have negative exponents in the top and in the bottom, so we're just going to flip them both. The bottom one will move to the top one will move to the bottom. So 2 to the negative 3 becomes 2 to the positive 3 in the denominator, and 3 to the negative 2 moves up to the top and becomes 3 squared. And these are each small enough to evaluate, so 3 squared is 9, 2 cubed is 8, so the whole thing is 9/8. The next example is exactly the same. We just have variable bases instead of having number bases. So we're going to flip the bottom one up, flip the top one down. So the top one goes to the denominator and becomes a to the m, and the bottom goes up to the top and becomes b to the n. And since these bases are not the same, I can't simplify this. So we just leave our answer like that. On the next example, I'm going to do this two ways. The quotient rule that we talked about earlier said that if you have a quotient where the bases are the same, then you can write your answer as base x and subtract the top power 3 minus the bottom power 5. If we do that, 3 minus 5 ends up being a negative 2, which has a negative exponent, and most likely we're going to want to write our answers with positive exponents only. So as a shortcut, or as an alternative, I am going to take the bigger power, 5, minus the smaller power, 3. 5 minus 3 is positive 2. The answer that we get, x squared, is going to go in the denominator because that's where the larger power was. So we take the larger power minus the smaller power and put your answer in the position of the larger power. So I have an x squared down in the bottom. We want a factor of 1 left over on the top to maintain that fraction. So two acceptable answers here would be 1 over x squared or x to the negative 2, and they mean exactly the same thing. However, the one on the left has a positive exponent, the one on the right has a negative. Okay? Next example, a to the 6th over a to the negative 4. You could use that quotient rule again. Oftentimes what I will do is whenever I see a negative exponent, I will automatically flip it. So in this case, a to the 4th is going to move up to the top. Now a to the 6th is going to stay in the top because it already has a positive exponent. So there's nothing left in the denominator anymore except a 1, which you don't even have to write. To simplify this, these two terms have the same base, so we should be able to simplify them. When you multiply the bases, you get to add exponents, so 6 plus 4 gives me a to the 10th. On the next example, I have 3 to the 8th, y to the 5th, over 3 to the 10th, y squared. Now the 3's have a common base, and the y's have a common base. So that means I need to simplify each of those. Since I've got 1's on top and bottom, we're going to be using that subtraction rule for our quotient. And to make this a little bit shorter with a little less writing, I'm going to use my shortcut and take the higher power minus the smaller power and put my answer where the larger power started. So if I deal with my 3's first, 10 is the bigger power. So 10 minus 8 would be 2, so I'm going to put my base 3 to the second power in the denominator since that's where the 10 was. For the y's, the larger power is on the top, the 5. 5 minus 2 is 3, so I'm going to have y to the third, and it's going to be in the top because that's where the bigger power was. Then for my final answer, you would want to evaluate and simplify what 3 squared is, so this turns into y cubed over 9. Okay, on these next examples we have some outer powers which we want to distribute. So remember, whenever you're distributing a power inside, it gets distributed to every term. And if something already has a power on the inside, you're using that power to a power rule, so you're going to be multiplying all your powers together. So x to the negative 4 times x to the x to the negative 4 times negative 3 power gives you x to the positive 12. 2 times negative 3 is going to give me y to the negative 6, and negative 5 times negative 3 gives me z to the 15. Now, I don't want to leave any negative exponents in my answer, so this is almost done, but not quite. I have this y to the negative 6. I don't want a negative exponent, so I just flip it down. So this y to the negative 6 turns into a y to the positive 6. And any terms that already had positive exponents, like my x's and my z's, they are going to stay put. So x to the 12th and z to the 15th stay where they started. Since I only have one x, one y, and one z term, this is simplified. Okay, on the next example we're going to do the same thing, but be sure to distribute that negative 3 power to everything. That includes the negative, the 2, the x, the y in the bottom, and the x in the bottom. So let's start with that negative out front. When you are taking a negative, remember to just look at the power and say, is it even or is it odd? And a power of 3, even though it has a negative there, a 3 power is an odd power. So a negative raised to an odd power is going to stay negative. 2 doesn't have a power already, so that 2 is going to get raised to the negative 3 power. X already has a power, so we're going to multiply negative 3 times negative 3 becomes positive 9. And y squared raised to the negative 3, multiplying those powers, 2 times negative 3 is a negative 6. In the denominator, negative 3 times negative 3 gives me y to the 9th, and 5 times negative 3 is negative 15, so I have x to the negative 15. Now we wouldn't want to leave our answer like this because I have negative exponents, so anything with a negative exponent needs to get flipped. So this gets moved down, this y gets moved down, and the x is going to get moved up. So we have a negative. The 2 to the negative 3 gets moved to the denominator. The x to the 9th on top is already a positive power, so it's going to stay in the top. Y to the negative 6 gets flipped down to the bottom, so now I've done everything on top so far. The y to the 9th that was in the bottom is already positive, so it stays put. And the x to the negative 15 is going to flip up to the top and become positive. So here's my new simplified expression so far with no negative exponents. The last thing we need to do here is combine our x's and our y's and simplify that 2 cubed. The x's here are both on top, so we're multiplying their bases. If your x's are on the same level, then you're just going to be adding those powers together. So 9 plus 15 is 24. That negative will just stay out front. So the top becomes negative x to the 24. In the denominator, those y's are also on the same level, so we're just going to be adding those powers. 6 plus 9 is 15, so we have a y to the 15th. And 2 cubed is 2 times 2 times 2, so that becomes 8. So my simplified answer, negative x to the 24 over 8 y to the 15th. Okay, for our next example, we're going to take this fraction and raise it to the second power. So remember that when you're raising something to a power, you need to make sure that you distribute that power across to everything inside of the parentheses. That includes any negatives, any numbers, any x's, and any y's. So we're going to want to distribute this 2 to the negative, to the 3, to the x, to the y, and to the x. Now when you're dealing with negatives, negatives are easy. There's only 2 things that can happen. If you're raising a negative to an even power, it's going to disappear. If you're raising a negative to an odd power, it's going to stay in your final answer. So since this square is an even power, that means this negative is going to go away. So that's taken care of. Now we get to the 3. 3 is not raised to a power, so it's just going to be squared. And then for all the rest of these x's and y's, they already have powers. So these are going to become powers raised to a power. And the law of exponents for that says to multiply. So when I do x cubed to the second, that's going to be 3 times 2, which is 6. So that's going to give me an x to the 6th. For the y's, 2 times 2 is 4. So this is going to be y to the 4th on top. Then in the denominator, 3 times 2 is 6. So this is a y to the 6th. And negative 5 times 2 is negative 10, so x to the negative 10. Once I've distributed my powers, now I'm just going to be looking for any negative exponents that I might see. And the only negative exponent that we have is right here. And negative exponents, remember, flip or take a reciprocal, so this is just going to flip up to the top. All the rest of these are going to stay put because they already have positive exponents. So I'm just going to recopy 3 squared, x to the 6th, y to the 4th, and y to the 6th. Those all stay put, and then this x to the negative 10 flips up to the top and becomes x to the positive 10. Now to simplify, let's start with our x's first. We have an x to the 6th and an x to the 10th. They're both on the same level, so when you're multiplying the bases on the same level, you get to add exponents. So 6 plus 10 is going to give me an x to the 16th in the top. Then for my y's, they are on different levels, and when your y's are on different levels, that means you want to subtract the powers. To ensure that we end up with a positive exponent for our answer, you always want to take the bigger power minus the smaller power. So 6 minus 4 would be 2, and where we're going to put that answer is in the position of the bigger power, which was that 6 in the bottom. So 6 minus 4 is 2, so we should get a y squared, and it's going to go in the denominator. Finally, 3 squared is 9, so our final answer is 9x to the 16 all over y squared. For our next example, pretty similar. So first thing we're going to do right off the bat is distribute this cube to the negative, to the 4, to the x, and to the y, and then we're going to distribute that negative 3 across to the y and to the x. So with this negative in the numerator, we're raising it to an odd power. That means that negative is going to stick around in our final answer. So that negative is going to stay put. Then we get to our 4. 4, it doesn't have a power, so it's just going to adopt that cube and become 4 cubed. And then for the x's and the y's, they already have powers, so a power to a power, we're going to want to multiply. So negative 3 times 3 is going to give us an x to the negative 9, and 2 times 3 is 6, so that's going to give us a y to the 6th. In the denominator, negative 3 times negative 3 is positive 9, so y to the 9th, and 5 times negative 3 is negative 15. So here's what we have so far. Now we're looking for anything with a negative exponent. Now, sometimes this is confusing for students when they see a negative 4 cubed and they think that that's a negative exponent, so they should flip that 4 cubed down to the bottom. Be careful on that. Negative 4 cubed is different than 4 to the negative 3. When you have the negative up in the exponent, that's the kind where you flip, and that would become 1 over 4 cubed. Negative 4 cubed is just 4 cubed, which is 64, and negative. So this side would be negative 64. Different answers. Here the negative's out front, just like a coefficient, but the exponent was still positive. Over here the exponent was negative, so that's the kind where we flip. So to help avoid that confusion, whenever you see a negative like this, you might want to just put it way out front of your fraction and then kind of forget about it. It's going to carry through your answer, but you're not going to do any flipping with it. So when I see this 4 to the positive 3, since it's a positive 3 power, it's going to stay in the numerator. When I get to this x to the negative 9, however, that does have a negative exponent, so that should be flipping down to the numerator. Y to the positive 6 is already positive, so it stays in the top. Y to the positive 9 is positive, so it's going to stay in the bottom. And x to the negative 15 is negative, so it's going to flip up to the top. So now we shouldn't have any negative exponents. So to simplify, that negative that we had for our coefficient stays out front. And then for my x's, I have an x to the 15 on top and an x to the 9th on the bottom. So subtracting bigger power minus smaller power, 15 minus 9 is 6. The bigger power is on top, so that's where I should write my answer. So this is going to be an x to the 6th. For the y's, they are also on different levels, so we want to subtract. Bigger power minus smaller power, 9 minus 6 would be 3, and the answer goes in the bottom, so that's going to give me a y cubed. And then finally, that 4 cubed. 4 times 4 times 4 is 64, and it stays in the top. So my final answer, negative 64 x to the 6th all over y cubed. Now let's take a look at one more example just like this. So again, we have stuff raised to a power, so we want to distribute that power across to the negative, to the x, to the y, and to the z, and then for the negative 3 on the bottom, distribute it to the negative, to the 2, to the y, to the x, and to the z. So for this negative on top, we were raising it to a second power, which is an even power. So this negative is going to go away. Then we have x to the negative 4 raised to the second, multiplying those powers. That's going to give me an x to the negative 8. We have a y squared being raised to the second, so multiplying those powers gives me a y to the 4th. And then that z didn't have a power, so it's just going to stay z squared. Then in the denominator, this negative is being raised to a negative 3, or just an odd power because 3 is odd. So that negative is going to stay put, and I'm going to put that negative way out front. Then we have our 2 being raised to that negative 3. I kind of covered up my negative, but there is a negative in front of that 3. Then for the y, we have negative 2 times negative 3 would give me y to the positive 6. 4 times negative 3 gives me x to the negative 12. And negative 2 times negative 3 gives me z to the positive 6. So here's my new expression. Now we're looking for anything with a negative exponent in it. So I see one here, here, and here. Everything else has a positive power. So I'm going to leave my negative way out front. This x to the negative 8 flips to the denominator. The y to the 4th stays on top because it was positive, and the z squared stays on top. The 2 to the negative 3 flips up to the numerator and becomes 2 to the positive 3. The y to the 6th stays in the bottom, and the x to the negative 12 flips up to the top and becomes positive, and finally the z to the 6th stays in the denominator. So all of our negative powers are gone. Now let's start simplifying. I have that negative way out front. Let's start with our x's. I have an x to the 8th on the bottom and an x to the 12th on top. Different levels, so we want to subtract bigger power minus smaller power. 12 minus 8 is 4, and that is going to go in the numerator because that's where the bigger power was. For the y's, I have a y to the 4th over a y to the 6th. Again, different levels, so subtract. 6 minus 4 is 2, and that's going to go in the denominator. And then for my z's, I have a z squared over a z to the 6th. Subtracting, 6 minus 2 is 4, and that goes in the denominator. Finally, my 2 cubed, 2 times 2 times 2 is 8, and that was in the numerator. So my final answer is negative 8x to the 4th all over y squared z to the 4th. Now this last example on exponents is a little bit different. It's actually a substitution problem, but it's kind of a tricky one for students. We have the expression x to the negative 2 plus 3y to the negative 1, and we want to substitute in values for x and for y. What I often recommend on a problem like this is that before you substitute anything in for x and y, rewrite this initial expression without any negative exponents. Now what I'm going to write down next is incorrect, so just be careful that you understand why it's wrong. A lot of mistakes that I see on this kind of a problem are students trying to flip everything at once. So on a problem like this, a lot of times I'll see something like 1 over x squared plus 3y to the 1st, something like that, where students are trying to flip both the x and the y down to the bottom at the same time. Now that's incorrect because of this plus sign which is in between. We are not allowed to distribute powers across addition or subtraction. So what that means is we need to make sure that we flip the x's and the y's, but we have to do them independently of each other. So when I take x to the negative 2 and flip it, it's just going to become its own fraction, 1 over x squared. And when I flip 3y to the negative 1, only the y goes on the bottom because there's no parentheses, so only the y is being raised to the negative power. That 3 is not being raised to the negative power, so it's going to stay in the numerator. So 3y to the negative 1 becomes the fraction 3 over y. So you want to do these two separate expressions separately and then add their results together. So x to the negative 2 plus 3y to the negative 1 should be 1 over x squared plus 3 over y. That's the correct way to flip it. Once you've done that, now we're ready to substitute in our numbers for x and for y. And remember, when you're substituting in values, always use parentheses. So I'm going to substitute in negative 3 for this x, using parentheses, and I want to square the entire value of x, and that includes the negative. That's why those parentheses are important. Then for y, I want to substitute in a 2. So when I square the negative and the 3, this becomes 1 over 9, and notice that that's positive. And for my second fraction, 2's not being raised to a power, so it's just going to stay 3 over 2. Now because I had to flip my x's and my y's separately as two separate fractions, notice we get two separate fractions here. So the only way to add these two fractions together is to make sure that we get a common denominator first, which would want to be 18. So I am going to change these two fractions so they have this new common denominator. To go from 9 to 18 requires multiplying by 2. To balance it out, I'm going to multiply the top by 2, so this becomes 2/18. To go from 3/2 to a denominator of 18, I'd have to multiply the bottom by 9, so I have to balance it out by multiplying the top by 9. 3 times 9 is 27. So now that the two fractions have the same denominator, we can add the two tops together. 2 plus 27 is 29, and the denominator stays 18. Okay, today is scientific notation, and scientific notation uses exponents to write a shorthand notation for very large or very small numbers. This is used quite often in the sciences when you're dealing with numbers that are very, very big or very, very tiny. Here is the general form for scientific notation. You always want to have a single digit out front of your decimal point. It must be a non-zero digit. So 1, 2, 3, 4, 5, 6, 7, 8, or 9 needs to go in this first spot. Then you have your decimal point. After that decimal point, you can have any number of digits that you need, however many significant digits as are needed for the number. And then you're going to multiply that by a power of 10. The exponent on the power of 10 tells you whether this is going to be a large number or a small number. If it's a positive exponent, then you'll have big numbers. If it's a negative exponent, then you'll have a small number. So for example, if I wanted to take 5,600,000 and write it in scientific notation, the first thing that you want to recognize is where is the decimal place initially in the number. There isn't one written, so it's implied to be after that last zero. So what we need to do to get it into this general form is we need that decimal to be after the very first non-zero digit. So we want to move that decimal so that it's right after this 5. So I want 5.6. The zeros here are not considered significant digits, so I don't need to write all those zeros after the 6. So I want to change my decimal point and move it all the way over in between the 5 and the 6. How many places did it take to move? Well, I went 1, 2, 3, 4, 5, 6. The number of places that you moved is going to be your power of 10. So I want 5.6 times 10 to the 6th. Notice that 6 is positive, so that means this should be a large number, which it is. It's 5,600,000. So you want a positive exponent if your number is bigger than 1. Okay, if I saw 0.007, this is a small number, a number less than 1. So whatever exponent I come up with is going to be a negative exponent. Now first we want to figure out where to move our decimal to. So what you want to do for small numbers is move this decimal so that it goes right after the first non-zero digit. So I have to go past these two zeros and then past the 7 and stop right there. So I want 7 and then my decimal point. How many positions did I move my decimal? 1, 2, 3, but it was towards the right. So I'm going to use an exponent of -3 because remember this was supposed to be a small number. So 7 times 10 to the -3. Alright, the next example here. My decimal point for this very large number is after that last 0. I need to move it all the way to the front, right past that very first 9. So my decimal is going to be 9.994, and I need to I can ignore all those zeros. I'm just writing down the significant digits. So that 9.994 gets multiplied by a power of 10, and the exponent that I need would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So I need a power of 9. For the last example here, I have again another very small number. So I want to move my decimal point past all these zeros and stick it right after that very first non-zero digit. So right after that 5. So my decimal part will be 5.75 times the power of 10, and the power of 10 that I need is 1, 2, 3, 4, 5, 6. But since I was going to the right, this is going to be negative 6, so that I get my very small number. Okay, that's taking standard numbers and writing them in scientific notation. Now we are going to go in reverse. We're going to start in scientific notation and write it in standard form. So 8.8 times 10 to the 6th. This is a positive exponent, 6. So we know that this should be a large number. So to make the number get larger, we need to move the decimal to the right. To make it get bigger, we're going to add zeros on to the end. And I need to move the decimal 6 places to the right. So this decimal right now is between the 8 and the 8. So I have to go 1 spot past that first 8. That's 1 position. Then I need to go 5 more to get all the way up to 6. So here's 1, 2, 3, 4, 5, 6. All these empty places get filled with zeros. So this is going to be 8, 8, and then 5 zeros on the end. If you put your commas in there, that gives you 8,800,000, which is a nice large number, so that makes sense with our positive exponent. On this example here, the exponent is negative. So if the exponent is negative, then this should be a small number, and we want to move the decimal to the left this time to make the number get smaller. We want to put those zeros on the front instead of on the end. So we have to go 1 spot past the 8 to the left, and then we need to go 4 more places to get to 5. So here's 1, 2, 3, 4, 5. All these empty places get filled with zeros, and the decimal is going to be right in the front. So this becomes 0.00089. And there's our very small number. Okay, this last example here is kind of a trick question because look at the exponent, it's a 0. This would mean we want to move our decimal 0 places. So if you want to move your decimal 0 places, it's not going to move at all. So this should stay 8.6. Another way to think about this is using that 0 exponent law that we talked about at the beginning of our notes. Anything to the 0 is 1. So 8.6 times 1 is going to stay 8.6. Okay, to finish off, we're just going to talk about how you can multiply numbers in scientific notation and how you can divide numbers in scientific notation. So here we have 8 times 10 to the 6th times 2 times 10 to the 3rd. Now the easiest way to do this multiplication would be to multiply like terms with like terms. You could expand this out to 8 million, expand this out to 2,000, and then multiply from there and convert your answer back to scientific notation. That's a lot of work, so we're going to use a shortcut. We're going to do the 8 times the 2, so the coefficient times the coefficient. 8 times 2 is 16. Then we're going to take the power of 10 times the power of 10, and that's going to get multiplied by our 16. Now remember, if you have 10 to the 6th times 10 to the 3rd, those 10s have the same base, So what do we get to do with the exponents when you multiply the bases together? Remember, you add. So 6 plus 3 makes this 10 to the 9th. Now we have a slight problem with our answer here. This is not considered scientific notation because look at where the decimal is. We don't really see it, but it's implied to be after that 6. And the decimal is supposed to be after a single digit, not after our 2 digits of 16. So to fix this, the long way to do this would be to rewrite this back into standard form. So that means putting all those zeros back in. Since this is a power of 9, a positive power, that means we want a large number and we want to move our decimal to the right 9 places. So if the decimal is after the 6, moving it 9 places to the right means I'm going to be adding 9 zeros. So very, very large number. Now let's convert that back into scientific notation. The decimal is after this last 0. We want it to be between the 1 and the 6. So we want 1.6. So how many positions do I have to move? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is now 10 to the 10th. So the long way is to take your answer, which wasn't quite in scientific notation, expand it all out, and then put it back into correct scientific notation. The shortcut is to notice that if I wanted to move this decimal just one spot over, that makes 16 get smaller and turns it into a 1.6. So if I'm making the front number get smaller, I have to balance out the power by making the power bigger. So from 9 to 10, I move the decimal 1 smaller for the front, so I make the power 1 bigger on that exponent. So that's kind of the shortcut. Alright, let's try another one, another multiplication problem. We're going to multiply the coefficient times the coefficient. 4 times 2 is 8. And that's going to get multiplied by a power of 10. We want 10 to the negative 3 times 10 to the 7. So remember, when you multiply same base, you get to add the exponents. Negative 3 plus 7 is 4. And this is in correct scientific notation because the decimal is implied to be right after that single digit 8. So we don't have to do anything else with our answer. We're done. Okay, the last two examples, this time we're going to divide. So we're going to divide the coefficient with the coefficient, and then we're going to divide the power of 10 with the power of 10. 12 divided by 4 is 3. That's going to get multiplied by a power of 10. Now be careful here. When we do these powers of 10s, the easiest way to do these is to follow that quotient rule, which says take your power of 10, your exponent on the top, and subtract the power on the bottom. In these problems with scientific notation, it's okay to have a negative exponent. So you don't need to do the bigger power minus the smaller power. Just take the top power, which in this case is negative 4, minus the bottom power. You want to be really, really careful with your negatives because otherwise you might make a mistake. So negative 4 on top minus the negative 3 on the bottom gives us a double negative. Negative 4 plus 3 is negative 1. So the new power of 10 that I want is 10 to the negative 1. And this is in correct scientific notation, so I'm done. Okay, last example, same thing. We're going to divide the coefficients with the coefficients, and then we're going to divide the powers of 10. 9.5 divided by 5. You can do that on your calculator. That gives you 1.9 times top power, which is negative 1, minus the bottom power, which was 3. Negative 1 minus 3 is negative 4, so the power of 10 that we want is negative 4. And remember, it's okay to have negative exponents when you're doing scientific notation, so this answer is good to go. Alright, that concludes our lesson on laws of exponents in scientific notation. Good luck.